So solving systems of equations is when we're going to have two linear equations and we want to find a point or a value for x and y that works for both equations at the same time. So solving a system of equations is finding this point that works for both. So let's just look at how we could check that. So if I have a coordinate to determine whether or not this is the solution for this system of equations, what I'm going to do is plug it into both. And the idea is it should work for both of them. So x plus y equals 7. So I'm going to take 4 plus 3 and see, does that equal 7? Which it certainly does. So it works for that first equation, but it also has to work for the second equation. As soon as it doesn't work for one of them, then it isn't a solution. So 4 minus 3, and does that equal 1? It does. With questions like this, make sure you write an answer. Like, just this isn't enough. We would need to actually answer, like, we're determining whether or not the ordered pair is a solution. Yes, it is a solution. That would be our final answer, and that work up above would be the proof. Let's look at this more complicated system of equations, and we're going to check it with this point right here. So I'm going to take 2 times our x value, which is 2, plus 3 times our y value, which is negative 3, and I want to see, does that equal negative 5? So I'm using the symbol here. I didn't explain it before. I like to put a question mark over the equal sign, and a lot of people in math do this when we're solving something that we're not sure whether or not it balances. So like when I check answers to things, and like here's kind of like checking an answer, put a question mark because I'm not sure if it actually is equal or not. So you might see me use this symbol, and you might see it around in other resources as well. So see, we have a positive 4, and then we have a negative 3 times 3, which is 9. And I see, does that equal negative 5? Which it does. So that works great. Plugging into the second equation, so we're going to have 7 times x, which is 2, and then minus 3 times y, which is negative 3, and does that equal 26? So we have 14 plus 9, and does that equal 26? Well, 14 plus 9 is 23, and that does not equal 26. So that coordinate there does not work for the second equation, which means it doesn't work for the system of equations. So no, this is not a solution. So what happened here was this point is a point on this line, 2x plus 3y equals negative 5. If I graph this line, we have a coordinate. But when we graph the second line, it doesn't have this same coordinate as part of it. However, in this first example, this coordinate works for both of them. So if I created graphs for them, we'd have this shared coordinate, which would show up as an intersection point. So for solving these systems of equations, we're going to look at solving them algebraically because that's the most accurate way to do it. Graphs are wonderful. It lets us see trends, but sometimes it can be hard to see exact values coming through with graphs. But we'll kind of start with graphs and then move on to the algebraic way of solving. But the idea is that graphically, this point is an intersection point of these two lines. Where we graph the two lines, it's going to be a point where they overlap with each other. So that's how we're going to solve systems of equations graphically, is we're going to look for this intersection point. So what we're going to do is graph both of the lines and then see where they intersect. So this is going to be good practice for graphing our linear equations. So y equals 2x minus 4. So this gives me a y-intercept of 0, negative 4. And for the slope, we have a slope of positive 2, which I won't write this every time now. I kind of talked through it, but that's telling me to go up 2, right 1 is the map that I want to follow. So let's go ahead and graph that line. So first I should set up my axes and put a scale, and then we'll be at -4, and then I'll have my slope of 2. Now, when you do these, you should really use graph paper. You can even, if you don't have graph paper, you can print off graphs. So if you have a printer at home, you can print graph paper off. If you just Google graph paper, something will pop up. You just want to be very detailed here, and then use a ruler. I can't recommend it enough. Because what will happen is if the line's a little wobbly or if it gets off a little bit, then you're going to end up with the incorrect answer here. So just try to be as exact as you can with these. So I'm going to graph. There's my y equals 2x minus 4. And then I need my second line. I'll do this one in blue so you can see the difference between them. So y equals x minus 30. So I'm going to have the coordinate 0, -3. And we're going to have a slope of 1. So that's going to tell me to go up 1, right 1. So 0, -3. I'm going to zoom in a little bit, so a little careful. So I'm here, and then up 1, right 1, and there I can actually see my intersection point. So while you're plotting points, it might be helpful. I'm going to just mark them a different color. And then 1, 1. I'm just going to get some points to graph my second line. Alright, so with that, I'm going to graph my second line here. That is my y equals -3. And then I'm looking for the intersection point, which is coming through as x is +1, y is -2. So what I'm going to do is write a conclusion that the solution is 1, -2. So with these, be sure to clearly state what the solution is, because you graph the points, you find that intersection point, but you need to show that you understand that that's actually the solution to the system. So we'll always have this kind of statement at the end of it. What you can do is check your answer, just like we kind of did up above there. Take this coordinate, plug it into both equations, and make sure it works for both. If it doesn't, then it means something wasn't graphed correctly. Alright, let's look at x minus y equals 4. So I'm going to solve for x here, solve for y, so I can get my y-intercept form. So I'm going to subtract, the slope-intercept form. Yeah, okay. Subtract x from both sides, so -x plus 4. Divide by -1. So I'll have y equals +x minus 4. So I'm going to have the coordinate 0, -4, and a slope of 1. I'm going to go ahead and get my other equation ready. X plus y equals 3, and solving for y, we'll have a y equals -x plus 3. So we're going to have a y-intercept of 0, +3, and a slope of -1. Alright, let's graph these points. So, I'm going to label my axes, x, y. I'm going to use a scale of 1 here. So, we'll have the coordinate 0, -4, and then it will have a slope of +1. So I'm just going to get some points drawn here. What can also be nice if you don't have exact graph paper or you aren't sure about your line, this is a case where drawing more points is helpful, because then you can see really where it's landing, and then you can really see that when you start graphing the second equation, where they intersect with each other, if you're mapping all of those points. So I'll have 0, +3, and then a slope of -1. So I mean is by graphing all of these points, then I can see where it crosses over. And what I can see is this is going to be kind of a weird one. But I'll show you how to check your answer. This is the case where it'd be nice to be solving algebraically to know for certain. But I'm going to show you where I'm going to guess a little bit, but then we can check our answer and make sure. Alright, so there's my second line. So the intersection is happening right here, and it looks like it's smack dab in the middle of that square. So what that would mean is for x going 1, 2, 3, and then I'm pretty much halfway into that square right there. So I'm going to put 3.5. I'm going to use decimals. And then for y, I'm at negative, and it looks about halfway down. So I'm going to go negative 0.5. Now, where I might start second guessing myself, even though I understand these slopes and they are landing right there. But if I was working with more strange numbers and strange slopes, I mean, that could be like 3.6 and a negative 0.4, and it would be hard to see from the graph, and that's where we'll look at solving algebraically. But let's double check this with Desmos. So Desmos, we have the scientific calculator, but they also have a graphing calculator. So let's look at graphing within Desmos. And what I'm going to do is I'm going to graph these 2 points, or sorry, these 2 lines. So I'm going to do x minus y equals 4, and x plus y equals 3. And what's nice about Desmos is intersection points kind of understands where they are. So if you click, you'll see these kind of important points show up, like it's showing the x-intercept and y-intercept for the red line. And if I click on the blue line, you can see my y-intercept, x-intercept is also highlighting this intersection point. And if you click on it, it'll kind of make it bold and you can really see it. But there's our 3.5, negative half. So with these, as you're graphing them, use this as a resource to check your graphs and check your intersection points. And in fact, when we get to solving algebraically, I might even go to this to check our answers kind of quickly with it. Instead of plugging everything and solving, you just graph them and it just comes down to that intersection point. Okay, so with that, I just need to make my little statement about what the solution is. So I'm going to say I'm not going to write it in red though. Let's say the solution is 3.5, negative half, negative 0.5. Alright. Okay, one more example here. So we have this 2y equals 4x minus 2. So I'm going to divide both sides by 2. So I'll leave me with y equals 2x minus 1. And with that, we're going to have the coordinate 0, negative 1, and a slope of 2. Let's go ahead and plot that. So x, y, and I know something about this graph where I'm going to be extra precise how I graph this. So negative 1, and then a slope of positive 2. Just going to get all those points. I know it's tedious, but accuracy helps. Okay, I'm going to graph this as carefully as I can because of what's going to happen next. Alright. Alright, some arrows, and there's our first line. Second line, 2x minus y equals negative 1. I'm going to subtract 2x from both sides. And I'm going to divide by negative 1, or you can think of that as multiplying by negative 1, either way. It's basically just going to switch the signs of everything. So 2x plus 1. So my intercept is going to be 0, 1, and I'm going to have a slope of 2. So I'm going to plot my point at positive 1, and then we're going to have a slope of 2. There, 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 there. And just plotting the points, what you should notice is that we never crossed that other line. And that is something special that's happening here. What we ended up with here are two parallel lines. Because we ended up with that same slope of 2, so keeping that they have the same slope and different y-intercepts. So we're seeing parallel lines here. And parallel lines never intersect with each other. No matter how far I graph this out, they will never intersect. So what that means is there aren't any solutions. If there aren't any intersection points, then there's no solution. So we would just write that no solution. The other special case that could happen here is you might end up graphing the same line twice. Like imagine if we had simplified this and this had ended up being a -1 for the y-intercept. Well, then when we went to graph it, we would just be graphing basically on top of that first line. In those cases, it's called a redundant case because you're just getting the same line out twice. But with that, you're basically intersecting absolutely everywhere on that line. So in those cases, we would say infinitely many solutions. Because absolutely anything would work because it would be on that line there. So that's how we solve with graphing. Again, we won't see these as much in the participation. I kind of focus on the algebraic method because again, when we get to these situations where we need to start using decimals and we might be confident in our decimal answers to really get the exact values, we want to solve these algebraically. But at least with this, we can see a visual of what we're doing.